another session on algorithms. I hope you are enjoying this series of sessions. And I told you right in the beginning, my primary objective is at the end of these sessions, you evaluate yourself on the basis of what you were before the beginning of this session. You will see the difference. If you can see, that would be my objective. Okay, as we all know, algorithms obviously operate on data. Algorithms obviously operate on data. Yes. Now that we are getting deeper and deeper into the study of algorithms as a problem-solving methodology, I thought that it's better to have some discussions on from the data structure perspective also. A few sessions earlier, I had talked a little bit about this, almost in the passing. But I thought that it's better to recapitulate and extend further whatever I had talked about, I think 3-4 sessions earlier. First of all, we all know that we are working on digital machines. Digital machine mean they operate on binary arithmetic, Boolean logic. So in their vocabulary, they have only 2 bits like 0 and 1. As for example, we are more habituated with digital system, decimal system, where we have 10 characters, 0 to 9. In computer paradigm, digital computer paradigm, they have only 2 characters, 0 and 1, to express everything. And whatever we do, what the computer stores, anything we provide as input in the form of 0 and 1. That is the bottom line. A few quick thoughts. You all are very much familiar with this, just for the sake of completeness. With 10 different characters, 0 to 9, we can have 10 square, that is 100 numbers, 100 integers. So with the 2 bits, how many we can make? 2 to the power 2, that is 4. If I have a decimal integer, say 45, shift it towards left, we have 450. Left shift 1 position means multiply by 10. Right shift 1 position means divide by 10. In binary, left shift by 1 position means multiply by 2. Right shift means division by 2. In fact, in typical computer science courses, we have 1 full paper on binary and digital logic, 1 full paper on data structure, 1 full paper on database management systems. Then there is data mining, data warehousing, all those. Just for reference, so that we are not completely out of the woods. We are not doing without understanding anything. I just wanted to share this. So computer understands bit. What is a bit? 0, 1. 1 individual character, just like we have a digit in decimal system, we have a bit in binary system. 8 bits make 1 byte. 8 bits make 1 byte. Why 8? I'm not going into details there. And several bytes make 1 word. Several bytes make 1 word. In terms of one of the parameters to understand the capability of a computer is its word size. That means what is the length of the word because the processor operates and accesses word-wise. As for example, 32-bit machine, that means word size is 32-bit. And what are the data types a computer has to store? There are various types, but some are primitive ones. What are the primitive ones? These are the fundamental ones. That means integer, real, Boolean, and character. Integer is generally stored in 2 bytes. Integer generally is stored in 2 bytes. 2 bytes means what? 16 bits, and 1 bit is reserved for sign. So basically 15 bits are available. So what is the maximum size of the integer a computer can store? What is the maximum value? What is the range of the value that 15 bits can accommodate? 2 to the power 15 minus 1. With 2, how many we can accommodate? 2 to the power 3, 2 minus 1, that is 3. 2 to the power 5, like that. So 2 to the power 15 minus 1, that is 32767 from the positive side, and minus 32768 from the negative side. Why one difference? That is because of the sign bit. I'm not going into details there. So that is the maximum size of an integer that can be stored in a computer. So if during any computation, the integer size goes beyond this level, you will find error. Some computers, some languages, they also have the facility of long integer, which is 4 bytes. So there you can have much longer, much larger integer. That is about integer. Real is actually fractional numbers. Those are stored in floating point representation. What is floating point representation? I've given an example. Say 4.1254. Before storing, it will be normalized. Normalized to the extent we will have the point, point placed to the extreme left. So whatever values we have will be only on the right side. So if we say for the sake of understanding, if we follow decimal system, 4.1254 can be considered as 0.41254 into 10 to the power 1. In computer paradigm, it will be stored in as exponent and mantissa, so that each of them individually becomes an integer. So in this case, exponent is 1 and mantissa is 41254. Obviously, I have explained in decimal. In computer, it will be in binary. So any real number that will be normalized like this, and then divided between exponent and mantissa, and then stored it. So one common practice is if we have a very large integer, we find difficulty in storing as an integer, we can store it in as a real number. But then say if we want to store something like 3,07,000 something. This is an integer, but while storing, I can place a decimal point to the extreme right. That's fine. There's nothing wrong between saying 15 and 15.0. But the problem is on one side with this floating point representation, even the integer can be stored, a very large integer can be stored as a real number. But what do we do with these values of course, we compute these values. And at the time of computation, these values will be treated as real numbers, not an integer. And since it is considered as a real number, in one of the last sessions, I have explained that error may flow if we go ahead with real values computation. Why? So 7 by 3. What is 7 by 3? 2 point and goes on. This is a infinitely long string. We cannot store the entire fractional value. At some point of time, we have to truncate. And if two real numbers or one integer and one real number gets keep on computing, this may accumulate reasonably large. So this is integer real. Boolean is if I declare a variable, and all these are computer uses this data as variables. So Boolean means the variable can take only two values, true or false, something like yes or no kind of thing. And then character, A, B, C, some special characters, all those. These are the characters. And each character is stored in 1 byte. Each character is stored in 1 byte. Generally, a Boolean also requires 1 byte unless you do something special, because Boolean does not require more than 1 bit. But usually, it is everything is stored in terms of bytes. So unless we do something smart, even a Boolean variable will also take 1 byte. So whatever we do using data, these are the primitive data types: integer, real, Boolean, and character. What do we do with these primitive data types? Let us see what are the, so we need some sort of derived data types. That means based on these primitive data types, we define some derived out of those. Very common of them are array, linked list, queue, stack. So what is an array? Just think of the way the books are stored in an almirah. Books are stored in an almirah. Only difference is in one row you have places for one book in one slot. So suppose one row can accommodate 70 books, and you divide that entire row into 70 slots of equal size. 70 slots of equal size. And then stored like that. This formation is known as an array. What are the characteristics of this? First of all, each slot has same size. Each slot has same size. And the total size required is obviously fixed. And you have to define it at the time of developing the array. As for example, when you design a bookshelf for your drawing room, you design the almirah first with that slots. So in one row, you can place 75 books, but you may not have 75 books at the same time. So some slots will remain vacant. Similarly, if you have to store more than 75 books, you cannot accommodate it. Even if there is space left, in the sense, since you have each slot some fixed size, each book may not require the entire size. But this is simple to understand, comprehend, and probably operate also. And in computer terminology, what does it mean? Say you have 100 integers to store somewhere. You define an array of 100 integers. Very simple. But remember, you have to define the array size to start with. That means if you have a provision for 100 integers, you cannot have 150 integers there. And at the same time, keeping a provision of 100 integers, if you use only 50, remaining 50 space will be unoccupied. And since each individual space has to be fixed in size, you cannot have different types of variables in the same array. Integer takes say 2 bytes, real takes maybe 4 bytes, character takes 1 byte. So whenever you define an array, you have to define an array of integers, array of reals. You cannot have an array where some are integers and some are real. On the advantages side, for array, for any data, there are two values. One is the content and the other is the address. Simple, you think about the mailing system. What is the mailing system? You mail one content and mail it to some address. Here is also like that. A location will have a content and will have an address. Have you ever thought of why email is so popular? Of course, it is instantaneous, but one major advantage is in a traditional mailing system, the address is defined by the location of the person, not the person himself per se. In email, the address is defined by the identity of the person. He may be anywhere in the world. So that is a big advantage. So if you look at the screen, if the starting address of the array is, I'm talking about address in the machine, is alpha 0 and width of each location is beta, you can easily see where the ith element of the ith element address will be alpha 0 plus I minus 1 into beta. First one will be alpha 0, second one will be alpha 0 plus beta, third one alpha 0 plus 2 beta, like that. And then to generalize it further, you can have two-dimensional array, which are generally known as matrices. But computer stores everything in a linear way. So even if we have a two-dimensional, three-dimensional array, the storage in machine is done in the one-dimensional form. So, and it's very simple. Think of the way you store your books in the Almeida. First row, second row, third row. So everything is fixed. So if you want to access any particular book, say in the third row, you can easily compute the access of, say, second book in the third row if you know the initial address. First row first, then second row, then third row, like that. So it can be easily computed. And since it can be easily computed, accessing any particular element within an array is independent of which element you are going to access. You don't have to go sequentially. If you know the address, straight away you go to the address and then do it. Of course, if you have to compute the address. Then comes linked list. Disadvantage of you can see in your this the example I have given. In this way, in the form of an array, first of all, what do we do with these derived data structures, derived data types? Lookup, insert, delete, and update. We want to look up, we want to delete, we want to insert, we have to update. Again, think of the book
structure, the way we store the books in the form of an array. If we have to insert a book within the array, it's difficult, it's problematic. We have to shift the books to the right, to the left, and then we have to enter it there. If we want to delete it, again, we look up, and then delete. So after some time, you will see, you will have several books and some slots are vacant. So unnecessary, some spaces are wasted, and that have to be recompacted. That have to be recompacted. So update is also again the same problem. To get rid of that, we can have another type of structure which is known as linked list. What is linked list? Here, every element in that series will have at its end the address of the next element. So if we want to address one particular, access one particular element, okay, I'll get back. If I have to address one particular, access one particular element, we have to go sequentially from one place to another. But remember, I do not have to reserve the entire space right at the beginning. Yes, there is a raised hand from somebody. Yes, go ahead. Unmute yourself and yes, question please. Okay, later on. So, so if the same set of integers, if we store as linked list, we do not have to fix the entire size. The elements did not have to be in the contiguous space. It can be all over the places. But you cannot gain something without losing something. Of course, you will lose losing something also, because here to access any intermediate point, we have to go sequentially. You cannot go like an array. I am moving very fast because I have to cover some algorithms later on. And then we have queue. Again, queue is very simple. Think of a queue is very common. You stand in a queue everywhere. There also you have a sequence of elements stored as a queue. So if it is stored as a queue, it is characterized the property of FIFO, first in, first out. So if you stand in a queue, the first one who joins the queue will be served first. That's the definition of a queue. First in, first out. That is the definition of a queue. And finally, stack. What is stack? Where these are stored in such a way that the element which has been introduced last will be treated first. Stack, LIFO, last in, first out. I have given a small picture. We have given a structure for storing the books like this in an array. Here, you can store the books like this, the way we carry the books in hand. If we carry 5 books in hand, how do we carry? One after another, another. And when we want, and how do we carry those? First one comes first, then second, then third, then fourth. And if we carry these 4 books, while taking out, which one we take first? The fourth one, the one which was introduced later. So this is a stack. The data is organized in such a way that the latest data is retrieved first. That is last in, first out. So array, linked list, queue, stack. I am just introducing this for those who are serious computer science students. I suggest very emphatically, don't ignore the topic data structure. Read, there are plenty of very good books. Horvit Sahani you can follow. Unless you understand data structures very well, you cannot understand algorithms also to that extent. And today, since, and which happens to be my area of research also at the moment, many algorithms are data driven, bottom up. So looking at the data, you have to define the algorithms. It would be extremely difficult for you to make a career in topics like data science, artificial intelligence, machine learning, and all those. So don't ignore the data structure and algorithms. Data structure is precursor to algorithms. So I give you an example from, again, typical mathematical world. Suppose for those, I think you all are familiar with what is known as factorial. What is factorial? Say factorial 6 is 6 into 5 into 4 into 3 into 2 into 1 or something like that. You will see these kind of problems have some specific nature. What is this? Factorial 6, I can easily compute by this series sequence of multiplications, no problem. Another way of doing it is, I know factorial 6 is 6 into factorial 5. So if I know factorial 5, I just multiply it by 6 and I get factorial 6. Again, factorial 5 is 5 into factorial 4. And we move down like that. So one way of computing is straight away multiply in sequence. And the other way is do it in steps. Think of the stack. I have to compute factorial 6. So what do? Instead of computing factorial 6, I put factorial 5 first in the stack. Then I put factorial 4, which comes on top of factorial 5, then factorial 3, then factorial 2, then factorial 1. And finally, I know factorial 1 is 1. So I am putting these intermediate steps in a stack. And once I am done, coming to a point where I know the result, I taking the values out from the stack. So I take out last in, first out. So I take out factorial 1, which is 1. Then comes factorial 2. I can compute factorial 2 now. Then comes factorial 3. Then comes factorial 4. Then comes factorial 5. So these kind of computation, these kind of algorithms to solve a problem is known as recursion. Otherwise, simple one is iteration. So we can have iteration versus recursion. But obviously, all problems cannot have a recursive algorithm. Basic requirement for applicability of a recursive algorithm is the problem must be decomposable in sub-problems whose nature is exactly same as the nature of the original problem. Like nature doesn't change. If I'm supposed to have factorial 6, but take a factorial 4, nature of the problem, structure of the problem is same. So we use a stack, proceed like this. Another typical example is, say, you know Fibonacci sequence. What is Fibonacci sequence? Any integer in the sequence is the summation of previous two integers. The sequence grows like this: 1, 2, 2 plus 1 is 3, 3 plus 2 is 5, 3 plus 5 is 8, then 13, and then goes on. And this Fibonacci sequence is also very much used in many cases, including cryptography. So now
if you are supposed to, identify, say, 50th element in the Fibonacci sequence, whose first integer is the first number is 1 and second is 2. Straight away, you can expand the thing like that. On the other hand, if you know the 49th element, and then you can also go for the 50th element. This is like this, that just like our factorial problem, here also we put the problems in stack one at a time, and once we come to 1 and 2, the initial stages, I get the answer and then take the integers out of the stack and go ahead. So this kind of recursion is of immense utility in algorithm design. You must keep this in mind, understand that fully. Already we have discussed many algorithms, many algorithms we have discussed. You could have, if you think yourself, you can see that those algorithms, some of them also, may be designed in a recursive manner. Sometimes it helps to design many complex problems, which we apparently seems to be very complex, but if it can be decomposed like that in a recursive manner, it's easier to comprehend. Okay, iteration versus, and this is array, linked list, queue, stack. Just think yourself their relative advantages and disadvantages in terms of lookup, insert, delete, and update. How do you look up at an element? How do you insert an element? What are the issues? How do you insert, how do you delete? How do you update? And remember, delete and update are basically secondary operations. For delete and update, first you have to look up. So this is a composite operation. So lookup is the basic operation, and insert is also basic operation. It has got nothing to do with other three. So these data types, you just think about yourself, which one is more suitable for which kind of jobs. And the other thing is, it's a very common question in computer science, IT, etc., that these data types are known as linear data types. Linear data types. Why? Because what is a line? How do you define a line? Line is a collection of a sequence of points. Is a sequence of points. Maybe straight line, maybe curved lines, whatever be the nature of the line, structure of the line, of a line, it would be a sequence of huge number of points. And what is the characteristics of this sequence? Any point within the line, except the first one and the last one, will have only one predecessor and one successor. Period. I see many have huge confusion about the definition of why these are known as linear data types. This is the primary reason. Think of array, linked list, queue, stack, all of them. Think of any element in that structure except the first or the second last. They will have exactly one successor and exactly one predecessor, just like a line. That's why these are known as linear data types. The moment we say linear data types, of course, we'll have non-linear data types. What are those non-linear data types? Graphs and trees. And these are also derived data types. These are also derived because their body includes integer, real, character, etc., etc. Before we go there, I give you another example. Like, we know how to store a character. A character is stored in 1 byte. Now, if we want to store the name of a person, how do I store it? If we store this in an array, array has fixed size.
So beforehand, we have to fix up the maximum number of characters which can be accommodated. Say 10, say 20. Once we fix that up and my name is smaller than that, I'll be wasting some space. If my name is longer than that, you have to truncate. You may have faced this problem in many cases when you fill up a form in a machine. You give your name and then it's truncated somewhere. Why? Because it is stored as an array. But it can be stored as a linked list also. My name is Swapan, is one character, then link to W, then link to A, then link to P, and then like that. But then that array size doesn't apply. We can have it like this is known as a string. And at the in string, finally we have to give a terminator. Otherwise, how do I know that that is the end of the linked list? Linked list will have a terminator at the end. But as usual, the moment you have a variable size length, it is quite difficult to handle those. But it depends on the application. Now coming to this graphs, we have used graphs already in many cases. You know that, and this I have introduced a couple of sessions earlier, just for the sake of recapitulation. We know what is a graph. It's a set of vertices and a set of edges, V and E. Generally, we will assume this terminology. Mod V is N, that is N is the total number of vertices, and small e is the cardinality of capital E. This is the maximum number of, this is the number of edges. And I have drawn a small graph. How do I store this graph? Because I can store only in the form of integer, real, character, boolean, and like that. Those are the primitive. Then we have derived data types, array, linked list, and all those. So I have to store graph entries also with whatever we have. And before going into that, just see the nature of a graph. Generally, think of any node, it will have more than one successor, it will have more than one predecessor. May not be true, but some of them will have more than one successor and more than one predecessor. So which contradicts the characteristics of a line. So this cannot be considered as a linear data type. This is a non-linear data type. And we can express this in the form of incidence matrix and adjacency matrix. Matrices are two-dimensional array. And now we know how to store the two-dimensional array, how these are stored in the machine, how they are retrieved. These are self-explanatory. In incidence matrix, we have n number of rows and n number of columns, and we put a 1 whenever there is an age, and 0 when, oh sorry, sorry, I made one mistake. First one, oh sorry. This is, I'm talking about this adjacency matrix, not this one, adjacency matrix. It's fine. So if we have a self loop, something starting from 1 and ends at 1, we'll have 0, 1 in place of 0 here, 1 and 1. So some characteristics I'm saying, which you can easily understand using your common sense. If this is undirected, whenever there's an age between 2 and 3, obviously this is the same as 3 and 2. If this does not have any self loop like that, this adjacency matrix will be symmetric in the sense element ij will have the same element as ji. So if we have some crunch in storage space, we did not have to store the entire matrix. We can store only 50%. Make a cut along the diagonal and take upper diagonal or lower diagonal.
But if it does not have any self loop, no parallel edge, and undirected, that is very important. And here, this is incidence matrix. What is incidence matrix? On one side, we have nodes, and one side, we have edges. So we have, if A edge between 1 and 2, just see 2 ones. B is 1 and 3. We have 1 and 3 in the corresponding places. Just think about yourself. So this is incidence matrix. So size of the adjacency matrix will be n by n, that is n square. Size of incidence matrix will be n by e, because e is the number of edges. And what is the maximum size of e? If it is, I have not defined already. Connected graph means all the nodes are connected. You can go to any node from any other node. Complete graph means all the nodes are directly connected. All the nodes are directly connected by an edge between the two. So if we have n nodes, we can have n into n minus 1 by 2, nc2, number of edges at the most. And at the least, if this is a connected graph, it becomes a tree. We'll come to that later on. There, you cannot have any loop, and we will have n minus 1 edges. So maximum value of e is n square, and minimum value is n minus 1, depending on the situation, provided it doesn't have any self loop or any parallel edge. Directed graph, when the edges are directed. Weighted graph means when the values of the edges has some weight. The weight may be distance, the weight may be nature of the road, the weight carries some physical value, physical interpretation. If it's a piping network, diameter of the pipe, so many things. So those are the weights. Those are the weighted graph. So instead of 1, we have used this shortest path algorithm. We have used minimum spanning tree algorithms. If we have to represent that in an adjacency matrix, what do? In place of putting 1, I put the distance between the two nodes in its place, which not only signifies that they are connected by an edge, at the same time, it also conveys the weight of the distance in this case. Those are weighted graph. Just a minute. And we can have more than one weight for any particular age also. So in the worst case scenario, incidence matrix will have n into e, that means n cube number of elements. And then the best case scenario, it will have n into n minus 1, that is n square. In adjacency matrix, it will always have n square. Another way of representation is adjacency list. Adjacency list. What is adjacency list? You just think yourself, you will find that for this particular graph, we'll have a series of arrays. Series of arrays, each of size e. E is the number of edges. For any particular edge, you will have a source node, you will have an end node. Say start with 1, A. It has 1 and 2. So we have 2 arrays. 1 goes in the first array, 2 goes in the second array. Next comes B, 1 and 3. 1 goes there and 3 comes here. Then 1, 4, where is C? D is 1, 4. So 1 goes there, 4 comes here. Just see whether, but this is how it is done. So there it were matrices. Now it is a sequence of arrays. Now what is the maximum size of this array? E is the number of edges. So E is nothing more than n minus 1.
At the most, it can be n minus 1. So total space required is, even if it is n squared maximum, then n squared plus n squared. But that is the worst case scenario. And another advantage is, if we have, instead of just being connected, if this is weighted as well, we can have some weights and have one more array, 1, 2, and then third array will be the distance between 1 and 2. No problem. If this is directed, no problem. You make it a point that the first array is the source node and second array is the destination node. And we can have sequence of arrays. And if we have sequence of arrays, total representation will take E plus E plus E plus E. So in terms of the order of E, which has worst case, in the worst case scenario, will be n squared. Whereas adjacency matrix is always n squared. Here in incidence matrix, it is worst case n cube, in the best case n squared. So in terms of space, adjacency list will be much better. In terms of representation also, it is easier. It is easier to include weights. So this is how. But generally, you will see, for algorithms we generally cover, we prefer to use adjacency matrix. Unless otherwise specified, we will assume that the graph is stored as an adjacency matrix. And our algorithm works on the basis of adjacency matrix. Reason is very simple. First of all, this is a square matrix. And for those who are familiar with matrix algebra, it's much easier to handle square matrices than with the matrices which are not square in nature. That means where n and m are same. And for adjacency list, handling adjacency lists is a bit clumsy. But again, some algorithms use that. But during our discussions, if we don't say anything, we will go by that, go by adjacency matrix. And we have already discussed tree is a special kind of graph which is connected. That means each node to each node there exists one and only one path. Remember difference between path and edge? Edge is between two adjacent two neighboring nodes, and path is the sequence of edges for going from one node to another node. And since there is one and only one path between any two nodes, it cannot have any cycle in it, and it can be proved that in such a case E will be n minus 1. And one special kind of tree which is very commonly used is binary tree. So where, because it's a tree, it follows whatever characteristics we have said. Beyond that, and you see this is not linear because the criteria of linearity is not satisfied here. So in a binary tree is what? Where every node will have at most two children. This is how the tree is structured. And the node at the top is known as the root. And the node at the bottom level is known as the leaf. And in between we have intermediate nodes. So we have root, we have leaves, and we have intermediate nodes. And if this is a binary tree, it can have at most, remember the word, I'm using the word at most, 2 children. If each node in the tree, excepting the leaf nodes, has exactly 2 children, then it is known as a complete binary tree. So if it is a binary tree, level 0, we have only one node. Level 2, we have 2 nodes. 2 to the power n minus 1, that is 2. Level 3, we have 4 nodes. Level 4, we have, it will go on like this, 2 to the power n order. So as the tree grows,
Finally, in any case, the leaves will be of the order of 2 to the power n, exponential order. You will see that today we are talking about coronavirus and all those spreading propensity, etc., etc. If the number grows like this, very soon it becomes huge. Just think of 2 to the power 15. We have just told you right now, 32768. So if one infected person can infect 20 persons from root, consider the person as root, and then we have 20 children, and then from each of that 20 we come down to another 20. Just think of what will happen if in the process, if it goes for 3-4 levels. You don't have to go beyond that. Even 3-4 levels, this will be beyond any type of control, because the number grows completely exponentially. Okay, so in this background, I think, I hope, Prem, are you there?
Yes, sir.
Can I take another 15-20 minutes?
Yes, sir. Yes, sir. Sure, sir. Yes, sir.
Because in this background, I have to cover 2 very important algorithms with huge usage. Okay. Now, let's get back to our typical algorithm design. I really love this design of algorithms because it tests your strength in innovation, strength in creativity. You need not have to be a genius in mathematics for that. Of course, you got to have strong mathematical background to analyze the thing. Otherwise, you may not understand which algorithm is good and which algorithm is bad, which is average. That's a different thing. But you need to have ingenuity. That's why you think of in any field, why Shevak is considered so great? Because innovation. Think of some poems, some football players. I'm sure many of you are watching Europa Cup. You see the kind of innovation comes from the games. So design of algorithms has a huge treats the person with, actually challenges the intellectuality, innovative power, creativity of an individual. But yes, you need to have some background. Otherwise, you can't do this. You cannot think about it. So that's why today we have discussed, some of which is basically a repetition about the data structure. Okay, now let us discuss. That's why I won't feel good if we don't discuss at least some algorithm before we wind up today. Graph connectivity and graph traversal. Towards the top left, we have a graph 1, 2, 3, 4, 5, 6, 7, 8 nodes, and you see the edges. I am in node 1, and I want to search for, say, node 6 or node 8. How do I reach there? Differentiate between the problem of shortest path and this problem. This is a problem of search. The question of distance doesn't matter. I'm not bothered about the distance. I want to search. That means I have to hop from one node to another node, then another node, and like that. And how do I reach that node? And the reason is very simple. In many applications, the cost of the path is not determined by the distance, physical distance between the edges,
Cost is defined by the number of hops I have to make in between. Why? If I have to transmit an electronic message from, say, one node to another node, distance travel has hardly any bearing on the total time, total cost. It's the number of nodes, because the maximum time is consumed within the node, intermediate nodes. Maximum time is consumed within the intermediate nodes. So, in many examples, the metric for the cost of a path from I to G is the number of nodes we have to traverse in between, not the distance, not the distance. In many other cases, of course, the distance may be there, and we have already discussed Dijkstra's algorithm there. So now these can be done in two specific ways. One is known as breadth first search, and the other is depth first search. For those students who are interested in studying artificial intelligence, data science, these are basically the alphabets of those disciplines. So please listen to me very, very carefully. First, try to understand how the algorithms work. In many areas, you will find applications of these algorithms either directly or in some other form. Just like Dijkstra also is applicable in some other cases. But these are absolute necessity for discussions on data science, algorithm, artificial intelligence, and all. So, how do I move? Listen to me. I'm again saying, listen to me very carefully. I start with, I'm discussing BFS, breadth first search. I start with node 1. This is level 0. Then, what are its nearest neighbors? Complete all of them. 2, 3. Simple. Once we go, and every stage, I mark the nodes which I have already discovered. So at every stage, we go one level down, and in the process, whatever nodes I have discovered, put a mark there so that we do not do it again. So I've come to 1 and 2. Now 1 cell. I come to 2 and 3. And I mark 1, 2, and 3, all 3 together. Now we level 1, or say it's level 2. This is level 1. From 2, where can we go? 3, 4, and 5. Now 3 is already discovered. Put a dotted line between 2 and 3. But 4 and 5 are newly discovered. So 4 and 5 comes under 2. 4 and 5 comes under 2. Now, what is my next step? I have next level, I have 4 and 5. Oh, there's only one mistake. There should be one dotted line between 4 and 5. I made it here. I forgot it. So when I'm in 4, 2, 3 के बाद, what is the next level? 4. From 4, I have only 5. 2 से तो हमें आए हैं. So 5 is already there. I have nothing to do. So please put a dotted line there. Think of, there should be a dotted line here between 4 and 5 because there's a connectivity. The dotted line. And then 5. From 5, I can go to 3 and 6. But 3 is already discovered. So put a dotted line. But 6 is new. So I come down to 6. Then 3 is already, I have come to 3. From 3, we have 7. we have 8, 3, 7, and 8. So they are at the same level. When that is complete, also we have 5, we can go down to 6, then go to 7. There is a connectivity between 7 and 8. 8 is already discovered, so put a dash. Put a dash. And then from 8, nothing to do. So you just do not consider the dotted lines. Just do not consider the dotted lines. Then we have a tree corresponding to this graph with 1 as the root. And it is a connected graph. It's a tree, it's a connected graph. And you know what are the nodes you have to pass in between. You have to pass in between to reach a particular node. How do you go to 6? 1, 2, 5, 8, 6. And there will be 1 and only 1. So this is known as search tree. This is known as search tree. So this is a huge problem in computer networks. Huge problem. That is basically on the basis of number of nodes to be crossed for traversing from one node to another node. And imagine social network, billions of nodes. In a social network, in WhatsApp, you have sent a message to someone who is in New York. How to go? Distance doesn't matter because it's an electronic message goes by, okay, speed of light, but the number of nodes are important. And the way we have gone, this is known as breadth first search. Okay, BFS. The other way we can do the same thing is known as depth first search. This is slightly difficult to understand. So again, listen to me even more carefully. Again, I am developing a search tree. Previously, we have done in one way. Now we are doing it in a different way. How is it? I start with 1, level 1. I go to the next level. Now, previously what we did in the next level, we have covered all the nodes in the same level before going another level down. That is why this is breadth first. Here, when we go to the next level, I may have several nodes in the next level directly connected. I can take any one of them. But the one I take, immediately that becomes my present status. From that node, I go to the next level and leave the other node in the same level unmarked. Clear? That means in breadth first, from 1, when I come to 2, before going further, I have to cover 3 also because they are at the same level. We are going breadth-wise. Now we are going depth-wise. So from 1, once I come to 2, I have to go below 2 and leave 3 as it is. As a jockey, when I see that I cannot move further below, I backtrack, go to the higher level, and then start again. So once in depth first, we start with 1 and 2. We could have started with 1 and 3 also, no problem. So we start with 1 and 2, but now we don't consider 3 because now I am in 2, not in 1. From 2, I have 4 and 5. I have 4, 5, 3. We have 3, 4, 5 from 2 because only the marked nodes are now 1 and 2. Everything else is unmarked. From 2, I can see 3, 4, 5. I can take any one of them. So I take 3. Come to 3. The moment I come to 3, I forget 2. Now I have only 3 is my present status. From 3, I can go to so many places. Out of that, I see 3 to 1. 1 is already marked. I won't go there because it's already marked. I always go to some unmarked place, and those marked places will also mark with a dotted line. From 3, I can go anywhere, but say I come to 5. So now 5 becomes my what? Present node. The moment 5 becomes my present node, from 5, I can go to where? 3 to 4. 5, I can go to, why I have given 1 there? 3 to 4. So this is a mistake. 5 to 1 is not there. Sorry. This one is mistake. 5 to 1 is not there. So from 5, I can go to 3 to 4. But all these 3 is just upper already connected. So from 5, I go to 4 times. 5 to 4, I come to 4. And these are connectivity. 5 to 1 is also connected. 5 to 1 is not connected. So this will not be there. Sorry. This one, 5 to 1, just remove it. And then 5 to 4 and also 5 to 6. Now, since 6 is not there, I cannot go anywhere else. I go back to 5. From 5, as I said, if we reach at a point where we cannot go further, we move backwards. From 6, we cannot go any further, move backwards to 5. Again, from 5, we cannot move any further back. So we go back to 3. Now, in 3, again, we can move forward. We come to 7. Come to 7. But after 7, we can go to 8 and we can go to 3. From 7, we can go to, but 8 is not already there. So we can put, so why there are some differences? Because depending on which one you take first, the shape of the curve may change the way it evolves. Finally, it will be the same. Finally, just like finally, it will be the same. But the way it evolves, that may vary depending on which one you choose out of several alternatives. Depending on how you choose amongst several alternatives. But you can see that this is how we keep on progressing. This is how we keep on progressing. But naturally, this will be a different tree compared to your BFS. So BFS and DFS will give you different tree, but they will represent the same graph. And they will represent the same initial graph, no problem. So, so to recapitulate, I tell you again that if 3 to 1, this, remember this 5 to 1, just forget this. This is not there because there's a connectivity with 5 to 1. That was a mistake. I did it quite fast, didn't follow. Look at it. But what is the methodology? In BFS method, I start from the root, come to the next level. Next level means those who are directly connected. So we consider all of them first before going later on. In depth first, say from the first level, I have 3 points to go in the next level. I can choose anyone, no problem. I can choose anyone. But once I choose anyone, I forget the others in the same level.
From that, we go to the next level, which are connected to that, and go ahead. And in both the cases, and in the second case, in the depth first case, the moment we go like this, after a certain time, if I find that I've come to a node from where we can move further, then I go back to the previous node from where I had come. And remember that previous node may have several nodes there which were uncovered in my forward pass. So now we go to another node in the same level and proceed with same thing. And at every stage, whenever I discover a node, I mark it. So if at any stage I have a connectivity with a node which is already marked, put a dotted arrow there. Because that is already marked. Marked means there is already a path discovered from one to that particular node. Nothing to discover, nothing to discover. When we do not have anything new to discover, but there is a path, or there is an edge, put a dotted line. The idea is we are generating a tree, and in a tree, any 2 points will have one and exactly one path. So if a node is already discovered, there's no point in discovering another path, because that will violate the characteristics of a tree. And how far do we proceed? Till we have discovered all the end nodes. Till we have all the end nodes. Remember, these processes will vary, will be applicable only for connected graph. If we have some paths, some nodes which are not connected at all, they cannot be covered in this way. Obviously, they are not connected with anything. So these are BFS and DFS. So as usual, today also we have covered quite a lot, and subsequently I am feeling a bit free in discussing some more algorithms, because now we know a little bit of how the data is stored. We know what is recursion. We know what is the difference between recursion and iteration. We know how arrays, matrices, linked list, and all those are stored, how the graphs are stored, and also we know what is the distance between two nodes, not necessarily summation of the edge lengths. It could be in terms of the number of nodes that have to be traversed for reaching a node J from node I. And we'll have plenty of applications, plenty of applications in real life problems, for designing algorithms, applications of these graph traversals, even the previous ones that Kruskal, Prim, then I think we have already covered quite a lot. Prim's algorithm, Kruskal's algorithm, Dijkstra's algorithm. I hope you are enjoying, because we are getting into a bit more deep into the subject. But yes, I was wondering why I made the mistake. This dot will be from 3 to 1, not 5 to 1. Just I'm putting my hand. 5, it's not 5 to 1, it will be 3 to 1. Okay. I have to rush to another meeting, but that's okay. So I think that's all for today. Prem?
Yes, sir.
Somebody
Yes,
who
sir.
raised his hand was asking something, but tell him to, I'm saying again and again, please send the questions to the coordinator. We will take it up before the commencement of the next class. Otherwise, the flow of the talk gets disturbed sometimes, because we are not in an interactive mode. If we are all in interactive mode, I in fact love this. And I'm sure you will have plenty of questions on these issues. And I'm also sure that if you are
computer science or IT or computer application students, you may have studied all these already, but there's nothing wrong in studying it again. Okay.